We're now going to turn our attention to that question I asked in the Gauss's lemma video on the polynomial t to the 16 plus t to the 15 and so on. And so let's give it a name first. We're going to define what are called cyclotomic polynomials, and the standard notation is this capital phi. And what phi n of x is, or phi n of t, I should say, we're using t, is it's the product over all 1 less than or equal to k less than or equal to n of terms where the GCD of k and n is 1, t minus e to the 2 pi I k over n. Now that's a mouthful. All we're doing is we're looking at the product of all t minus a primitive nth root of unity. So for example, phi 2 of t, or sorry, phi 2 of t, there's only one primitive nth root of unity. It's a primitive second root of unity, it's -1. So it's going to be t minus minus 1 is t plus 1. Phi 3 of t is t squared plus t plus 1. If you multiply it out, you will see you get that. Phi 4 of t, well, the primitive fourth roots of unity are plus or minus I. Oops. T squared plus I, t plus I. And if you multiply this out, you get t squared plus 1. And phi 5 of t, you'll find is t to the 4th plus t cubed plus t squared plus t plus 1, and so on. And in fact, whenever n is prime, we know that every nth root of unity is a solution to this, but if n is prime, all of the nth root of unities that are not 1 are primitive because they're relatively prime to n, because everything less than n is relatively prime to it. So when n is prime, let's say n equals p, phi p of t is just t to the p minus 1 plus t to the p minus 2 plus t plus 1. It's the part that's left over after you do this regular factorization where you pull out the t minus 1. Okay? So when p is prime, the pth cyclotomic polynomial is the sum of the powers of t for all powers less than p. So in particular, if we scroll up past our proofs here, this guy is phi 17 of t. All right, so this polynomial that we're looking at is actually a cyclotomic polynomial. All right, so the question is well, when are when are the cyclotomic polynomials irreducible? And it turns out they're always irreducible over Q. We're only going to look at a special case of that. So we're going to start with a lemma to help us prove that special case. The lemma is the following. If P is prime, the binomial coefficient P choose R, which is of course P factorial over R factorial, P minus R factorial, is divisible by P if 1 less than or equal to R less than or equal to P minus 1. It of course is not divisible by P when R equals 0 and R equals P because it's 1 when R equals 0 and R equals P. So let's prove this real quick, and then we'll look at the cyclotomic irreducibility of these cyclotomic guys when P is prime. Proof of this is simple. If P is prime, all terms in the denominator are less than P. For any of R value in this range, right? Because if R is at least 1, then the largest possible number that shows up in this big product for the factorial is P minus 1. All those numbers are therefore going to be less than P. Thus, p is not canceled by the denominator. Sorry, I don't know if you hear that. My dog's crying in her sleep. All right, so p is not canceled by the denominator. So if it's not canceled, there's still a p in this expression, so it's divisible by p. Okay, so p divides this binomial coefficient. All right, great. Now we're going to go ahead and look at the following lemma, which will finally answer that question. If p is prime, then the polynomials where we start with p minus 1 as the exponent and we decrease in that fashion are irreducible. Well, this certain polynomial is irreducible over q. Okay, so let me just give you some examples. This is, of course, phi p of t. Phi 2 of t, which is t plus 1, is irreducible. Of course, it's irreducible. It's linear. Phi 3 of t is t squared plus t plus 1 is irreducible. Being irreducible here is equivalent to having no roots. It's pretty clear to see this has no roots. Phi 5 of t is where it starts to get a little bit more complicated. This is irreducible. And if we were to do this by hands, we would have to show no roots, and then we'd have to rule out quadratic factors, because this could factor as a product of quadratics. But we can just apply this lemma and see it's irreducible. And this phi 17 that we started with, this t to the 16 and so on, is also irreducible just by this lemma. We don't have to do all those 7 different cases. We can just apply the lemma. All right, so let's prove this lemma. And then after this, we'll have one more irreducibility criterion in the next video, and then that's it. And these are what we have. So proof. We will observe, of course, that f of t, as I've shown you already, is t to the p minus 1 over t minus 1, right? If I take this expression here, and we divide by t minus 1 with n equals p, we of course get what I have just written. So observe that. And we're going to do a change of variables. Let me even just be really clear that this is what we're starting with. We're going to set t to be 1 plus u. This is a linear change of variables. In particular, if f is irreducible after this linear change of variables, it must in fact be irreducible before the change in variables. Okay, so we're going to set t to be that. Then f of 1 plus u is f of t is 1 plus u to the p minus 1 over 1 plus u minus 1. So that's 1 plus u to the p minus, in parentheses, minus 1 over u. All right, let's multiply this out. How are we going to multiply out 1 plus u to the p? We're going to use the binomial theorem. So it's u to the p plus p choose 1, u to the p minus 1, all the way up to p choose p minus 1, u plus, of course, 1. That's this part. And then we're going to subtract 1 from that and divide everything by u. So if we subtract 1 from that, the 1's cancel. And if we divide everything by u, we're going to get the following: u to the p minus 1 plus p choose 1, u to the p minus 2, all the way up to p choose minus 1. And what do we notice? Well, these are binomial coefficients times powers of u, and moreover, the constant term p choose p minus 1, that's just p, right? So let's use orange. Well, okay, that's just p. And so what are we going to do? We're going to apply Eisenstein's criterion with Q equals P. Namely, P of course divides the constant term. Let me just go through them. P divides P, of course, so it divides the constant term, but of course P squared does not divide P. That's fine. P divides all of the other coefficients for 1 less than R less than or equal to P minus 1 by the lemma that we proved before this. And the leading coefficient is 1, and certainly P does not divide 1. Thus, f of 1 plus u is irreducible in U, so it must be irreducible in T as well. And this is true because we're doing a linear change of coordinates. We're not doing a quadratic change. Quadratic changes would mess up irreducibility. All right, and so the pth cyclotomic polynomial is irreducible, and it's a fact that we're not going to prove, but I encourage you to maybe look up a proof of, that all of the cyclotomic polynomials are irreducible.